So we will start this session with a presentation about uncertainty of meteorological observations. This is where everything starts because in a lot of meteorological products, observations are really the base. So in this first part, we will talk about the observations with some examples to know what we are talking about, and then we will address the question of what is an acceptable level of uncertainty. Just to have a global idea of what we are talking about, here are some meteorological parameters. In this presentation, I will focus on surface parameters because this is what I know best. And this is, I think, what talks to a lot of people. So we have here some basic parameters like pressure, temperature, humidity, wind, rain, radiation, some information about clouds and snow heights. And a lot of different information, you name it, if you want to have some other parameter. All these parameters are important for meteorological applications, but they are also important for other needs. So here we have some of the different use you can make of these meteorological observations. And of course, energy management and energetic applications are one of the important use that you can have with meteorological observations. When you are in need of meteorological observations, you have two basic ways to deal with that. A first way is an opportunistic way when you will use existing data to meet your need. For example, if you are trying to install a wind farm or a specific energetic system, before setting a new observing system, you will have a look of available informations, and you will try to figure out from this information where is the best place to install your wind farm. Then, when you will focus on a specific location, you may set a really specific observing system. These two approaches are really different, and in the first one, we will have a major issue in carrying information about uncertainty associated with the data, because data depends on use. Depends. Acceptable uncertainty depend on use. So when there is an observing system set for one need, maybe it will not meet your requirements when you try to use it in another need. So this is important to know about this information. Here is an example in the figure just below of a measurement of snow height with two different sensors. In the green line, you have a measurement made by ultrasonic detection in a basic sensor when you measure the time of flight of an ultrasonic wave. And in the green line, you have a measurement made with a laser, and you measure a difference of phase between the emitted and received signal for this specific laser. In these two systems, you can see different resolutions of the instrument. The ultrasonic sensor, represented by the green line, has about 1 centimeter resolution. When the red one, which is the laser one, has about half millimeter resolution. So in these two different systems, you can see in this timeline that the first available information from the sonic sensor occurred about at 16 during the day we are looking at, when you have an information about at 13 for the laser sensors. So if you use this sensor, for example, to monitor the snow height in a ski resort, the green line will be good enough because you are not interested in knowing that you have 1 more centimeters at 16. This is not really relevant for what you are trying to do. But for forecasters in airports, for example, you are really interested in knowing that there is snow sticking on the ground at 13, because this will have a lot of consequences for your operations on the airport. So this example shows us that the accuracy of the observations really depends on the use of the meteorological data. This example is one among a lot of different examples, and even for meteorological applications, you have really different needs. Forecasters often rely on a fresher information, but they are not as interested in accuracy as climatologists that are really the more exigent clients about accuracy. So this is really an important question. There is not a good level of accuracy or a good level of uncertainty. The right level of uncertainty depends on the use that you will have of the data. For generic requirements, the WMO has set some achievable measurement uncertainty that you may see on this line. This is for different requirements. We talked about forecasting, climatology, but there is also requirements of airports managers, farmers, and so on. And these requirements are the recommended achievable requirements that every country should try to have in its networks. But unfortunately, this is not really easy to meet these requirements, even when you have some good sensors. So for a lot of uses, you can cope with some requirements that are far below WMO requirements. We will see some example later on. Usually in a lot of meteorological agencies, we have a basic network of really good measurements that we try to be compliant with the WMO requirements. But we will have different networks that are less accurate, but that covers different needs, and that will be that will have more density. So after this first presentation about the question of the right level of uncertainty, which, as we saw, depends on the use of the observation, we will just address a short example about a really simple system, just to have a view of different sources of uncertainties. This basic system is based on a temperature measurement. This is a really basic sensor, which is a RTD of 100 ohms at 0 degrees. which is really the standards for a lot of meteorological agencies. And the sensor itself gives a maximum uncertainty of 1.15 degrees Celsius. This is not a major source of uncertainty in our system, as we will see further on. A second component of this observation system is the screen, because every temperature measurement should be protected from radiation, rain, and should be in a thermodynamical equilibrium with the rest of the atmosphere. In this screen that we use in our network, there is no power needed. That is interesting to have locations, remote locations far from energy sources. And the uncertainty at 95% confidence is minus 0.3 degrees Celsius and plus 0.7 degrees Celsius. This is an average screen. There are better screens, but this one is not bad. A third component of our observing system is an automatic weather stations that transforms and converts the signal from the sensors into a meteorological parameter and sends a meteorological message. These stations gives an uncertainty under 0.24 Celsius degrees because of analogical to digital converters and so on. And the fourth component of our systems, which is not really a component, but we will see that this is really important, is the location of our sensor and our systems. There is here an example of the sighting classification. We will go further on later to know what it is about. But there are rules you should respect to have good measurement and a good representation of what you are trying to measure with your system. So if you combine all these sources of uncertainties for a good sighting, and if you respect proper maintenance and calibration, this system will give you an uncertainty at 95% of confidence between 0.55 degrees Celsius and 0.85. So this is our basic uncertainty in Météo France network, but we can go a few slides before. This is absolutely not compliant with the WMO recommendations because we are far away from 0.2 degrees Celsius degrees. So this information is interesting, but this is not compliant with the WMO requirements. So we will have to add more information to this data to be sure that the user know what it is about and what is the accuracy of the measurement. So there is a really important issue about uncertainty management and the metadata management associated with this measurement. So to manage this information, we have two metadatas that will carry a lot of information. The first one is the sustained performance classifications, which is focused on the equipments and the operations of maintenance and calibration associated with this equipment, and a different metadata associated with the sighting, which is the environment classification. And these two metadatas combined can give you a maximum uncertainty and a really accurate information about accuracy. So the first one, the observing system has limits within itself. The sensors and the acquisition systems are designed for a maximum accuracy, and often the lower the uncertainty, the higher the price, of course. But this is one parameter of the uncertainty. Another parameter is that the uncertainty can change over time. And if you do not respect proper maintenance and calibration operations, you will have a worse accuracy of your system. Back to our example, for the sensor, the temperature sensor, to have this level of uncertainty of plus or minus 0.15 Celsius, you must have a control every 5 years of your sensor. If you do not respect that, there is a lot of cases when there is a time drift, and when the sensor does not meet the uncertainty requirements of 0.15 anymore. So this is an example where you have the equipment, and associated to this equipment, you have an operation that you must do to be sure you control your source of uncertainty. This is exactly the same for the screen. You should wash every year the screen and paint it every 2 years, because if you do not so, the screen, which is white to prevent the radiation from being absorbed by the screen, the screen becomes gray, or there is something in the screen that prevents the right function of the screen. So we have introduced this sustained performance classification to deal with the two aspects. The first one, the equipment, and the second one, the operation associated with this equipment, mainly maintenance and calibration, of course. So we have divided into 5 classes this metadata. The class A is a sensor and an equipment that associated with the maintenance require the WMO requirements, follow the WMO requirements, and we have it is doing worse when you go down to the later. And there is a class E used when you don't know the characteristic, especially when you use equipments that you have no information about. So in our example, we are in B class, and if we would like to meet the WMO requirement, we need a ventilated shield that requires power supply, and that is more expensive. So this is not that we use usually in our network. Here you have some example of for our basic network the different sustained performance classifications. And here is some little differences for station when you have someone in the station, which are not really important in France, and the station when you have only automated systems. So we are trying to close every man in the station because it is really expensive, and we will have about 1,500 automated stations and by the same time we have only 6 stations where there will be human people in the station. So this is really these are just seats there and more than 1,000 there. But the two differences we can focus on are these ones. The first one is the global radiation. We had examples by Laurent of some informations before in the morning. And to meet the WMO requirements, you need to swipe the sensor every day to make sure it is really clean and there is no dust in there. So if you have nobody there to do this operation, you cannot meet the requirement of WMO. So this is why we have place A. When you are in when you have someone that can swipe the sensor, and you are only place B when you have nobody there. So the equipment is important, but the maintenance and the different operations on the equipment are maybe also important. And this information is also relevant. This is for visibility. It's important to have an information of visibility on airports when you're trying to land planes. And the historical way to measure visibility is to have somebody that watch on some landmarks. And when you are using a human observation, you cannot really guess what is the right uncertainty, because it depends on the human and on many conditions. So we have used this E-class of we don't know to represent this information. The second metadata, which is also really important and maybe more important than the first one, is the environment of the measurement. And Alberto told us about an example. I will have a really close one to show you that this is maybe the most important parameter governing uncertainty. This is the sighting. In this example, you have about 150 kilometers eastward from Toulouse. You have the Mediterranean Sea, and you have this watchtower that is used to by coast guards to regulate sea traffic. And they have a need of wind information in this location. But this is just above a cliff, maybe a 100-meter cliff. And here is some simulations of the cliff effect. That is to say, for a 100-meter cliff, or 100 something, 100 feet, or this is not scale dependent. You will have a really important overestimation of the wind in the location that is maybe, let's say, 300 meters away from the cliff. So in this example, you are really close to this location, which is symboled as 1.7. And so this location really overestimate the wind that is in a more global view. So this is not, in fact, a bad measurement, but this is not a measurement that is representative of the large scale that is often the most important scale for meteorological uses. So this is not a bad measurement by itself, but you can not use it to feed your model or to make a forecast about, I don't know, 5 kilometers away, because this is not representative. But for the closed worlds, this is relevant information because it's representative of a measurement nearby this area. So this sighting classification is often the most important source of uncertainty. That's to say, with the state of art, the state of the art, sorry about that, of the instruments and equipments, you are often in one order of magnitude of uncertainty below the uncertainty you add with the sighting of your instrument. So this is maybe the most important parameter to monitor when you use the data. This is the sighting of the data. And like we did before with the sustained performance classification, we divided into 5 classes this metadata with class 1, a site that is a reference, and 5, a site where you shouldn't have meteorological observations. So we will see later on some example. Just before going further on the example, this classification is now becoming a standard at the WMO. This is something that was introduced 2 years ago at the WMO, but that were used earlier in France to classify the different location of our network. And this sighting classification will be standardized by the International Organization for Standardization within maybe a year or 2. This is a work in progress. So the sighting classification, as you can see it at the WMO in the WMO website, for example, is a sighting that is different for each parameter, because this is not the same requirement when you measure temperature or when you measure wind or I don't know, humidity, rain, whatever. There are often some little drawing that will show you geometries of the location of your instrument. For example, this classification is used for temperature and humidity, and you should avoid, of course, to have some obstacles that prevents from the energy from coming in this area, because you want to have a good representation of the atmosphere exposed to the radiation. You don't want to have heat sources. You don't want to have a concrete nearby, because this accumulates and this radiates a lot of heat, and you don't want to have a bad measurement due to that. You want to have low grass and low vegetations to prevent some humidity in the vegetations to disturb your measurement. And you want to avoid, of course, water sources nearby, because also this will cool down your system, and you will have a bad measurement. So this is one example of sighting classification. But there are many others. Of course, for radiation, you try to avoid any problems of shades on the sensor. This is pretty straightforward. For rain gauges is a little tricky, because the right rain gauges is a rain gauges a rain gauge, sorry about that, rain gauge with a fence to prevent wind to disturb the rain to go in your rain gauge. But this is sometimes hard to have a good classification. For example, a good classification for a rain gauge will be a forest when you have just a little hole when you will put your rain gauge, and then you will have a really good measurement because no wind will arise around the rain gauge, and you will be in a really good location. But this is not a good classification for every parameters except the rain. So this classification tries to cope with that and present classification that is based on open location. And the last example, this is the wind, where you try to measure wind away from obstacles, of course, to have no problem with fences or edges or so on. So back to our temperature example. In a class 3, which is an average site, this is not the worst, but this is not really good. The uncertainty of temperature at a confidence of 95% is between 1.2 and plus 1.5 Celsius degrees. And you have here the different sources of uncertainty. And you see that the site is really the more important source. So in many examples and in many real data that you will have to your use, the most important source of uncertainty is the site. That's important to remember. So I have an example really close to Alberto's example in Australia. This is at Toulouse Airport, and you have here the numbers of days when you have a southeastern wind at Toulouse, which is a strong wind that is not the synoptic wind, which is a west wind, but that is really important because it changed the way planes should land on Toulouse Airport. So this is an operational conditions, and for operational conditions are really important parameters to monitor. And we can see that this wind, which is a 10 meters high wind, increases along the time. You have the mean of the two time periods. And like we saw with Alberto example, this is due to an edge that has been cut down, and well, we have more southeastern wind now on Toulouse Airport. So this is important to have the story of a site when you work on climatology, and to know any change of instrument, any change of location, any change in the surroundings of the location, because simple example like that can show you that this is a source of uncertainty that is more important than the climatologic variation that you want to monitor, for example. So we saw that we have two main metadatas to figure out which is the uncertainty associated with an observation. But this works only for a well-working instrument, nominally working instrument. And of course, we have a failure, and we have some systems that are broken down. So here is an example that we had a few days ago in Toulon stations, which is a sensor going mad and giving really bad informations. But, well, this is a failure, okay? But there are different kind of failures, and we have, for example, failures that you can process, and then you can go after the processing to recover the missing data. And there are failures like that when you cannot do anything. So we are working on a third metadata to characterize failures and to characterize what you can do with bad data. If you can recover information totally or partially, and what you can do with that. Another source of uncertainty, I will go real fast on that, but it's good to know about it, is the messages and the way the information has been stored. Because when you use old informations to have a good knowledge of the climate or the variation of meteorological parameter on a site, you need to use old data. And the way meteorological data are stored, are coded, really depends on time and are made on really raw approximation. So, for example, a visibility of 5,600 meters will be coded only 5,000 meters, because you always want to give the pilot worse information than the real one. So you always go down to the lower information for the visibility information. But when you are trying to use it to know, I don't know, about haze or so on, this information you want to have an accuracy better than 5,000 meters. And maybe in this example, you will, if you don't know about the rules used to code the message, you will see, wow, maybe I'm between 4,050 and 500 and 5,500, but no, you are over 5,500. So it's really important to know the rules that are used to code messages, because otherwise you can do really bad use of the information. And often you can just find data that are the post-coded data to have raw information that will not be processed to the approximation like this visibility. You need to have access to the raw data. That is not the case for older data. So, well, if you use old data, this is important to know about that. For the last item of this presentation, I will go on a specific example of a way to mix two sets of data. The first set of data will be a data that is really accurate, but that has low density, and the other one is a high density data, but that is not really accurate. This example is real-time rain observation information. When we use two systems, the first one is a network of radar. We have about over 20 radars in France that give some information about rain. The good point is that the information is available everywhere in France, because radar provides specialized information, but the quality is not already that good. And we have rain gauges. We have about 1,000 automatic rain gauges that provide real-time informations that are more accurate, but that only provides local information, as you can guess. So we developed a mixed product. Its nickname is Antelope, which combines the two informations and tries to give the best of the two. Here's one example of a large-scale event. So the right image is the radar raw information, and the left image is combined information. So you can see this is not only a smoother map you have here, because you have some really different information, for example, in this area and in this area. We can see that the radar totally underestimates the amount of precipitations here, whereas there is some precipitation in this area. So this way to combine the two information is a really powerful way to deal with limits of observing systems and to have a more cost-effective system than a system based only on one equipment. Here is another example for different events, convective events, when you have storms and so on. And here you have the radar information, and here you have the specialized information, including the rain gauges. And in this example, in the previous example, this is really important to have rain gauges because they are accurate and they can give you a better information of what's going on. And in this information, you have really interest in having a radar because convective events are really localized and you cannot monitor such events only with rain gauges. So the two ways of dealing with this equipments are really powerful. So I'm about it for these presentations. We saw that we have some different sources of uncertainties. I tried to make the point that it's important to carry metadata with the data, because when you use the data, it's important to know which accuracy you can attach to the data. And the second point is that citing is the key, like Alberto told us in his introduction. And this is often the best way and the most cost-effective way to improve your measurements. And the third point is that combining different single informations into a global system is sometimes a better way to improve your system than only focusing on one equipment and one systems, because you can have really you can take the best of the different systems that are available. So thank you for your attention, and if you have questions, I will be happy to answer them.